Hey guys, how's it going?
Hello.
How's everyone doing?
Good, how you doing?
I'm all right. Another day. All right, so do you guys have any questions from last time? Or any questions at all? I think it looks like most of you did quiz 1. So I think I'll try and grade all of it today. I think quiz 2, like some of you asked me to extend the dates, and I'll extend quiz 2 a little bit. We just kind of want to stay up to date, but I mean, I'm okay with you submitting it a little bit later. And then I'll probably work on your quiz 3 today as well. Any questions before we start? No, everyone's good. All right, so we did chapter 1.5 last time. We're going to skip 1.6. So 1.6 is mostly just applications of what we've done so far. But I mean, we're just gonna do theory. All right, so we'll start 1.7 today in our textbook. So chapter 1.7 deals with the concept of linear independence of vectors or of columns in a matrix. So I think today we'll just do 1.7. All right, and it's not a very complicated concept, but if it's new to you, I mean, it will take a little bit of kind of absorbing. But overall, it shouldn't be too bad. So kind of the definition of linear independence. So if I have an index set of vectors in Rn, right? So I have vectors with n components, and I can have any number of vectors. I have p vectors, like v1, v2, all the way to vp, and all of those have n components. So we're going to say that this set of vectors is said to be linearly independent if the vector equation, so I'm kind of taking a general linear combination of all of those vectors, right? x1, x2, all the way to xp, just some constants multiplied by vectors, everything summed up. And if this adds up to a 0 vector, so if this sum has only the trivial solution, remember trivial solution means that all of my xi's have to be equal to 0. All right, the trivial solution, it's just a 0 solution, right? My vector x equals to 0, 0, 0, 0, right? And because it's an Rn, I basically have n zeros in my vector, right? So if this vector equation only has a trivial solution, then we're going to say that this set of vectors is linearly independent. And the set is called linearly dependent if there exist weights C1, C2, Cp, so kind of there exist values for x1, x2, all the way to xp. Right? Not all 0, such that this equation equals to 0 vector. Right? So basically the difference is for linear independence, if I'm taking this linear combination, I must have all of my constants to be equal to 0. But if some of those constants are not 0, then we're going to say that the set of vectors is linearly dependent. Right, so we'll do a lot of examples, right, to kind of be able to understand like why we need linear independence and exactly what is this concept. All right, so but kind of this is our basic definition of what it means for a set of vectors to be linearly independent and what it means to be linearly dependent. All right, and in general, the way to do this is you kind of be solving this linear equation and looking at, do I only have the trivial solution or do I have some non-trivial solutions? Right, so if I do have non-trivial solutions, we're going to call this relationship a linear dependence relation. Right, so if I can't find the values for those constants that are not all 0, some of them can't be 0, but if some of them are not 0, and this adds up to a 0 vector, this would be called our linear dependence relationship. And kind of another way to look at it, our set of vectors is linearly dependent if and only if it is not linearly independent, right? So it's one or the other. It's either linearly dependent or linearly independent. Does that make sense? Right, so and we'll do a lot of examples, so you guys see exactly what this means for vectors to be linearly dependent or independent. Right, so we'll start with one example. I'll take so I'm taking those three vectors here. So my three vectors in R3, right? I have three components. So all of those guys belong to R3, and I have three vectors in R3. Right, and I want to determine if this set is linearly independent or if it's linearly dependent. Right, so by my definition, the set is going to be linearly independent if this vector equation only have the trivial solution, meaning this will only be true if all of the x1, x2, and x3 are all 0. Right, and kind of going back to the previous chapters, trying to solve this vector equation really is equivalent to putting my vectors v1, v2, and v3 into my augmented matrix form, with the augmented column being my 0 vector here. Right, and I forgot the vector notation. Right, so it's basically equivalent statement, just phrased a little bit differently, and for us it's much easier to use this definition in order to solve this equation. Because I mean, if you start solving this equation, at the end of the day, you're still going to end up having to put everything into augmented matrix form and solving it with your elementary row operations. Right, so if I write down my augmented matrix, I'm basically just copying down my columns from my vectors, right? First column, second column, third column, and my augmented column is just the 0 column. Right, so I'm going to have 1, 2, 3, 4, 5, 6, 2, 1, 0, and the augmented column is column of all zeros, right? Because I'm solving this vector equation. So are you guys all good with row operations? Maybe I'll do this one more time, and maybe we'll start kind of skipping it a little bit in order to save some time. All right, so when I'm solving this augmented matrix, and again, I'm starting with the first pivot column. I have pivot in this first position 1, and I'm trying to eliminate everything below. So I'm going to have row 2 minus twice row 1, right? 2 minus 2 times 1 to eliminate 2. And row 3, I will replace with row 3 minus 3 times row 1 to eliminate this 3. Right, so if I carry out these computations, I'm going to have 1, 4, 2, 0. First row is unchanged. Then in the second row, I'll have 0 like I wanted. Then minus 3, 0. And in the last row, I'm going to have 0, right? 3 minus 1 times 3. I'm going to have minus 6, and 0. All right, so I'm just like what we did before, right? I'm solving my augmented matrix by performing my elementary row operations. And next, I have my first pivot column, I have my second pivot column. So I want to eliminate this minus 6. All right, so maybe I'll do my row. Maybe I'll rescale it first. Let me rescale. So it's a little bit easier. All right, I'm going to take my row 2, divide by minus 3, and I'm going to take row 3 and divide by minus 6. All right, it would be a little bit easier. So I have 1, 4, 2, 0, 0, 1, 1, 0, and 0, 1, 1, 0. All right, so it looks like my second and my third rows are exactly the same. All right, so I'm going to, again, look at my pivot columns and eliminate everything below the 1, below my pivot position in the second column. So I'm going to do row 3, replace row 3 with row 3 minus row 2, right, to eliminate this 1. And so I write down what I have. So first row is the same, 1, 4, 2, 0. Then I have 0, 1, 1, 0, and 0, 0, 0, 0. That makes sense? So from here, we're ready to start solving for possible x1, x2, and x3. Right, so the third row doesn't give us anything. If I remember my rule for my pivot columns, right, I have a pivot in the first column, and I have a pivot in the second column. But in the third column, I do not have the pivot. So I know that because in the third column there is no pivot, my x3 is going to be free variable. All right, so from that, I already know I'm going to have infinitely many solutions here. All right, so maybe I'll let my x3 be equal to some value alpha, where alpha can be any real number. All right, so it's my free variable. And then going to my other rows, right, second row, I'm going to have my x2, right, plus x3 equals to 0, right, or x2 equals to minus x3, and x3 is alpha, so x2 equals to minus alpha. Going to my first row, right, I have x1 plus 4x2 plus 2x3 equals to 0. And solving for x1, I have x1 equals to minus 4x2 and minus 2x3. And I know x2 and I know x3, so I can plug in my alphas here. Minus 4, x2 is minus alpha, and minus 2, x3, and x3 is alpha. All right, so I'm going to have a plus 4 minus 2, or plus 2 alpha. Right? So I'm getting that my solution here, vector x, in terms of alphas is 2 alpha, right, minus alpha and alpha, where alpha can be any real number. Yeah. So now if I want to kind of go back to the question I was looking for an answer for, does this vector equation have only the trivial solution? No, it doesn't, right? It also has infinitely many solutions because I didn't have a pivot in the third column, a free variable. So I don't just have the trivial solution, I have infinitely many solutions. So what does that mean for us in terms of linear independence? From definition, my set is linearly independent if this vector equation only has the trivial solution, which is not the case here, right? I have infinitely many solutions. So not just the trivial solution. I can conclude that my set of vectors, v1, v2, and v3, is linearly dependent Yeah. And since it's linearly dependent, I can also find my linear dependence relationship, right? So basically, when we did this, we solved for the values of my C1, C2, and C3, right, for which my linear combination would be equal to 0, right? So we can even write this down. And I mean, alpha could be any real number. So, I mean, you can just take some real number alpha that gives you a non-trivial solution x, right? So maybe I'll pick something simple, like alpha equals to 1, right? If alpha equals to 1, then my x equals to 2 times 1 minus 1 and 1, right? And that basically means that when I'm taking this linear combination with my given values of x1, x2, and x3, I'm going to get a 0 vector. So 2x1 multiplied by v1, 1, 2, and 3, minus, right, minus 1 times 4, 5, 6, right, my v2, and then plus 1 multiplied by v3, 2, 1, and 0. We can check, does this equal to 0? Because here I have 2 times v1 minus v2 and plus v3. Right, so if it's linearly dependent, it should be equal to 0. Right, and we can check, right? 2 times 1, 2, minus 4 plus 2. First component is 0. 4 minus 5 plus 1, 0. 2 times 3, 6, minus 6 equals to 0. Right, so this is my linear dependence relation. Right, this is the relation that basically gives me the values of the constants I need to multiply my vectors by so that I can sum everything up to 0. So this is linear dependence relation. That makes sense? So whenever you're given a set of vectors and you want to figure out if they're linearly dependent or independent, you're basically trying to solve this kind of homogeneous equation, right? If this homogeneous equation only has the trivial solution, then my set of vectors is linearly independent. But if I have some free variables, meaning I have infinitely many solutions, then you can basically pick some value alpha to be able to write down this linear combination of my vectors that actually add up to 0. And those constants are not all 0. Well, in this case, they're all not 0, but they don't have to all be not 0. Just some of them have to be not 0. That makes sense? All right. Let's look further. So we'll be doing this kind of all day today. So hopefully this will make a little bit more sense towards the end. So and remember how our matrix equation, matrix A times vector x equals to 0 is basically equivalent to this vector equation. So just two different ways of writing this. Right? Multiplication of A by vector x is the same as kind of taking linear combination of columns of A. Right? So A consists of columns A1, A2, all the way to AN. And x is the vector with components x1 through xn. Right? So what we did just now, we can also apply to columns of matrices, right? And we can say that the columns of the matrix A are linearly independent, right? So I'm basically looking at columns of matrix A as vectors now. So instead of like V1 all the way through VP, I'm just taking columns of A, A1 through AN, right? So columns of matrix are linearly independent if and only if this matrix equation only has the trivial solution. So it's kind of the same concept, just applied to kind of matrix equation form versus the vector equation form. That makes sense? And just like before, right, we can look at kind of each linear dependence relation. So if I do have my columns of the matrix A being linearly dependent, I should be able to write down kind of this linear combination of my columns equal to a 0 vector for some non-zero values of x1, x2, all the way to xn, right? So for linearly dependent columns, I should have a non-trivial solution for this vector equation, or a non-trivial solution for this matrix equation. And so otherwise, it's pretty much the same concept here. All right, so let's do an example here for the matrix. So if I'm given the matrix and I want to determine if the columns of the matrix A are linearly independent. So it's just like what we did before. I'm looking at my columns as basically vectors, right? If I look at my matrix A, it has 3 columns. So I have column A1, A2, and A3. Now, and I know that my columns will be linearly independent if the matrix equation AX equals to 0, only trivial solution, right, which is equivalent to having a vector equation x1, A1 plus x2, A2 plus x3, A3 equals to 0 vector, only trivial solution. So this we need for linear independence. Right, so both of those things will lead to linear independence. And just like before, both of those statements are also equivalent to basically looking at my augmented matrix where I'm taking columns A1, A2, and A3, and my augmented column is my zero column. Right, only the trivial solution. And so, again, just three different ways to look at the same exact concept. And if we only have trivial solution, then we have linear independence. And again, our augmented matrix form is just the easiest way to solve this. All right, so just like before, we will construct our augmented matrix. Right, so I'm just copying my matrix A, 0, 1, 5, 1, 2, 8, 4, minus 1, 0. And my augmented column is just all zeros. Make sense? So, and again, are you guys all good with elementary row operations? Do you want to kind of do this again, or should we, we just skip the steps? Anyone?
I think it's all good.
Okay. Yes, I mean, then something like this, you would interchange like the first and second row to get your pivot position. Maybe we'll do this one. So I'll interchange row 1 and row 2. Because remember, you can interchange rows, you can multiply a row by any number, any real number, and you can kind of add multiple of one row to another row. And I'll do just the first step, 1, 2, minus 1, 0. I'm interchanging the first two rows, 0, 1, 4, 0, and then 5, 8, 0, 0. So our first pivot, first column, I'll eliminate 5. So I'll just kind of skip those steps. So do your elementary row operations until you get to row echelon form. So once you get to row echelon form, you will have 1, 2, minus 1, 0. You have on the second row 0, 1, 4, 0. And my last row, I mean, that was just basically one operation here. You're going to end up with 0, 0, 1, and 0. All right. So I'm kind of going to your row echelon form. All right. So what do we have here? If I examine, I have pivot in the first column, I have pivot in the second column, and I have pivot in the third column. So each row on each column, I can say each row of A has a pivot. So what does this mean in terms of our variables? Well, that means that I can solve for x3 uniquely, I can solve for x2 uniquely, and I can solve for x1 uniquely, right? So all three variables are basic. So I have no free variables. Right, and if I have no free variables, that means that I have one unique solution. Right? But if I have one unique solution, remember, this is my homogeneous problem, right? Ax equals to 0. And homogeneous problem always have the 0 solution, right? If I have matrix A multiplied by some vector x and that equals to a 0 vector, my x equals to 0 is always a solution. And since I already know x equals 0 is a solution, here I know that I only have one unique solution. My trivial solution is going to be my unique solution. So x equals to 0 is the only solution. So this is my trivial solution. And so by definition of linear independence, I can conclude, because this matrix equation only has the trivial solution, confirmed, 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 I can conclude that the columns of my matrix A of A are linearly independent. Yeah, so here we do have linear independence. That makes sense? Not too bad. All right. So, okay, so now let's kind of dig in a little bit further into this concept of linear independence. And if it's a little bit easier to understand it if you start with some very, very simple sets of vectors. So what's the simplest possible set of vectors I can have? Well, I can have a set of just one vector. So what if my set of vectors is just one vector v? Is the set of one vector linearly independent or linearly dependent? Right, so if my vector v is not a zero vector, then still you're just following a definition, right? The definition of linear independence is that if I take a linear combination of all of the vectors in the set and that equals to 0, then I only have the trivial solution. And for one vector, that still applies, right? My linear combination of just one vector is constant times this one vector. I'm setting this equal to 0, and my solution here would just be one real value of x. So if v is not 0, I really do only have the trivial solution, right? If I had like x1 multiplied by some vector that's not 0, right? Maybe 1, 0, 0, right? Or any vector with non-zero values here. Then in order for this to be equal to 0, 0, 0, I mean, I must have x1 equals to 0 because this would be equal to x1, this equals to 0 equals to 0. I still need to have x1 equal to 0. So for non-zero vector v, I only have the trivial solution if I have one vector. And this would mean that this is going to be linearly independent. The other option is maybe I do have just one vector and that one vector happens to be the zero vector. In this case, if I have some unknown x1 multiplied by 0 vector equals to 0, well, here I will have infinitely many solutions because if I have x1 multiplied by all zeros, right, by vector multiplication, I have x1 times 0, right, x1 times 0, x1 times 0. I mean, this will be equal to 0, 0, 0, regardless of what the value of x1 is, right, for all x1 real numbers, right? Any number times 0 is 0. So for this case, I will have that since my linear combination is possible for any real value x multiplied by 0 vector will be equal to 0 vector. I have infinitely many solutions. So in this case, my set of one vector v will be linearly dependent. And for vector b that's not 0, my set will be linearly independent. So it's kind of a very, very simple case, but I mean, it just tells us that, you know, if I have one vector, I really can't take the 0 vector because 0 vector will always be linearly dependent. That makes sense? It's a kind of a, like a degenerate case, but I'm kind of starting small and then moving forward. So what about if I have now two vectors in my set? So we'll do this by example. So in this example, I have v1 and v2, two vectors. And I want to determine if the set of those two vectors, v1 and v2, is linearly dependent or independent. Right. So, and again, go to your definition. What does it mean for two vectors to be linearly dependent or independent? That would mean that if I take linear combination, right, x1 times v1 plus x2 times v2, and set this equal to 0 vector, if I can find x1 and x2 not all 0, such that this is true, then my set will be linearly dependent. And with two with the case of two vectors, it's actually pretty simple because what you can do is just examine what's going on here. If I look at this relationship, I mean, I can always just put one of those x1 or x2 on the other side, right? x1 times v1 equals to minus x2 times v2, right? x1 is some constant, x2 is some constant. So if x1 is not 0, I can divide by x1. If x2 is not 0, I can divide by x2. But really, this linear dependence relationship just tells me that v1 is some multiple of v2 if they're linearly dependent. And in this case, if I examine this, okay, my first component is 3 in v1. My first component is 6. 6 is 2 times 3. First component is 1, first component is 2, right? 2 is 1 times 2. So kind of by examining it, it looks like v1 is just a multiple of v2, right? v2 is twice v1. Right? So since v2 is a multiple of v1, I can actually rewrite this more in my kind of like linear dependence relation form. Just put everything on one side. I will have 2v1 minus v2 equals to 0. Right? And I do have my linear dependence relation. Linearly dependent. Right, where I can look at, and if 2 is my x1 and my x2 equals to minus 1. So I am able to find the x1 equals to 2, x2 equals to minus 1, such that when I take this linear combination, this equals to a 0 vector, which means that my set is linearly dependent. Right? But in this case, in the case of two vectors, you can just do this by inspection, right? Just look at the values and see if maybe those values are multiples of each other, right? Is my v2 here is exactly twice v1. So that would mean that they're linearly dependent. And if I modify one of those vectors a little bit, right? So over here, if I take, right, so I changed 1 to 2. Now it's going to be different. Now they're no longer multiples of one another, right? So I can start with writing down my possible linear combination, set it equal to 0, right? So I have x1 times v1 plus x2 times v2 equals to 0, right? So if I rewrite this with my vectors, I have x1 times v1, which is 3 and 2, plus x2 times v2, which has components 6 and 2, and this must be equal to 0, 0. Now, so now if this set was linearly dependent, then, I mean, either both x1 and x2 are not 0, or at least one of them is not 0. So suppose maybe my x1 is not 0. If x1 is not 0, then I can basically put this guy on the right-hand side of the equation. So I would have x1 times v1 equals to minus x2 times v2. And for non-zero x1, I can divide by x1. So then I will have v1 equals to minus x2 divided by x1 times v2. Right? So if x1 was not equal to 0, then I should have that v1 is minus x2 over x1 is just some constant, right? So v1 would have to be some constant multiple of v2. But in this case, it's not the case, right? Because my first component, 3 and 6, 6 is twice 3, but 2 is not twice 2. So kind of by inspection here, v1 and the 2 are not multiples of one another, of each other. So this is not true. Can't be. right? So, and if it can't be, then my x1 must be equal to 0. And you can do the same with x2, right? If my x2 is not equal to 0, then similarly, I'm just taking this relation and I can divide by x2 or minus x2. So this will give me that my v2 now equals to minus x1 divided by x2 times v1. So it's kind of the same thing here, right? If x2 is not 0, then v2 is going to be some constant multiple of v1. But because by inspection we know that it's not the case, right? v1 is not multiple of v2, v2 is not multiple of v1. You can also conclude that this can't be, which implies that my x2 must be equal to 0. So x1 must be equal to 0, x2 must be equal to 0. And if both x1 and x2 are 0, that would mean that I only have the trivial solution. And since I only have the trivial solution, that would mean that my two vectors here, v1 and v2, must be linearly independent. So why did we do this here? You don't really have to do all of those steps whenever you're dealing with the set of just two vectors. The one thing to notice here is we were kind of able to tell if it's linearly dependent or independent just by inspection. The only thing you have to do is just look at your two vectors and check if they're multiples of one another. Can I get v2 by multiplying v1 by some constant? Or can I get v1 by multiplying v2 just by some constant? In this first example, yes, we could have done that. So that would mean that set is linearly dependent. In the second example, v1 is not a multiple of v2 and one vice versa. So that would mean that this set is linearly independent. All right, so for two vectors, it kind of makes it's a little bit easier to understand what linear dependence or independence is. All right, dependence just means that they're multiples of one another. And independence means that they're not multiples of one another. That makes sense? We can summarize this concept here in the theorem just for the set of two vectors. All right, so the set of two vectors, v1 and v2. So any two vectors, I mean, the only restriction is they have to both belong to the same space. So if v1 is in Rn, then v2 is also in Rn, right? You can only compare, kind of like look at vectors that have the same number of components. So the set of two vectors is linearly dependent if at least one of the two vectors is a multiple of the other. So if they're multiples of one another. And the set of two vectors is linearly independent if and only if neither of the two vectors is a multiple of one another. So graphically, you can look at it as, all right, linearly dependent set. Right, if vectors are multiples of one another, they basically lie along the same line. Right, my v1 and v2 is just a rescaled version of v1. So v2 and v1 here are linearly dependent. But linearly independent vectors, that means that they're not multiples of one another, right? So my direction of the vectors is different, v1 and v2. That makes sense? Yeah. And again, for the set of just two vectors, you don't have to do any kind of rigorous derivation. You can always just do this by inspection, like check if v1 equals to some constant times v2, right? If that constant is not 0, then they're linearly dependent. Make sense? So for two vectors, very simple. Again, just check if they're multiples of one another. If they are linearly dependent, if they're not, then they're linearly independent. Yeah. All right, so for one vector or two vectors in a set, it makes sense, right? So now let's kind of go back and look at kind of the general set of vectors and how do we decide if that set is linearly dependent or independent. and kind of like more so conceptually, like what does it really mean? So we have a theorem, so an index set, right? So now I'm taking a set of more than 2 vectors, is linearly dependent if and only if at least one of the vectors is a linear combination of the others. Right, so we started with the definition of kind of taking linear combinations, and this equals to 0 only has the trivial solution. But now this is like a slightly different way to look at the same thing that kind of gives you a little bit more insight into exactly what it means for vectors to be linearly independent. All right, so since we have more than 2 vectors, for 2 vectors, that's just multiples of one another is what linear dependence is. But for more than 2, I mean, if maybe all of them are multiples of one another, it's a simple case. But it's the only condition, right? I can have a lot of different vectors, and for the set to be linearly dependent, really I only need kind of like one bad apple in the whole bunch, right? Even if just one of the vectors is a linear combination of a few other ones in a set, then my set would be linearly dependent. Right, so again, we'll do some examples to kind of dig into this concept. So it's a little bit like tricky to get it first, but once you get it, it's not that difficult. Right? Again, just remember, if I have a set of vectors, it's going to be linearly dependent if and only if at least one of the vectors is a linear combination of the others. Right, so maybe I would have like vector v3 in my set is a linear combination. Maybe it's like 3 times v1 plus 2 times v10, something like that. Right? That makes sense? Yeah. So then the whole set would be linearly dependent. Maybe all the way to like, maybe I have like 20 vectors in that whole set. So just because v3 is a linear combination of v1 and v10, the whole set would be linearly dependent. That makes sense? So it just takes one vector being a linear combination of some other vectors in that set for the set to be linearly dependent. So kind of another part of this theorem that's from your book. You can also say that if S, so the set of vectors, is linearly dependent, and we're assuming that the first vector is not equal to a 0 vector. So remember, a 0 vector is always going to be linearly dependent because I can multiply it by any non-zero number and still get a 0 in my sum. So then for some vj, so for some vector vj in my set, vj is going to be a linear combination of the preceding vectors. So why are we doing it this way? I mean, we'll do some examples, but the idea is if I have a bunch of vectors in my set, so if I have like v1, v2, v3, v4, v5, and so on, and say I determine that this whole set is linearly dependent, what I can do is I can start going through my vectors and comparing them. So I can look at v1 and v2 and see is this set independent or not. So v1 and v2, maybe I determine that it's independent. Then maybe I'll take more vectors. I'll take v1, v2, and v3. And I determine that it's independent. But then if I take v1, v2, and v3, and v4, this set is dependent. So what this would mean that by adding v4 to my v1, v2, and v3, my set becomes linearly dependent, which we will show in a little bit. That means that basically one of my vectors, or since I had v4, it became dependent. v4 is actually a linear combination of the other 3. All right, so v4 would be equal to c1 v1 plus c2 V2 plus C3, V3. So this is basically kind of the general idea of like why you write the definition this way, right? Because now, because this set is linearly dependent, my V4, this extra vector that I added, is basically a linear combination of the preceding three. That makes sense? But again, we'll do some examples and hopefully it'll make a little bit more sense, right? And also something to note that this does not mean that every vector in a linearly dependent set is a linear combination of the other vectors, right? So you can have a linearly dependent set, and I mean, maybe one vector is a linear combination of the others, but it doesn't mean that all of the vectors are linear combinations of others. Like, for example, here, V1, V2, and V3 are all independent, so neither one of the three is linear combination of the other two. But if I take V1 through V4, it becomes dependent because V4 is a linear combination of the other three, but I can't really say much else. All right, but again, we'll do some examples to kind of get a hang of it. I think like the good way to look at it is my set could be linearly dependent, and it's not because all of those vectors are dependent on one another. It's just because one of the vectors is kind of redundant. I already have enough vectors in my set in order to generate this vector by taking linear combinations. So let's do one example here. So I have a set of 4 vectors, right? V1 is 4, 4, V2 is -1, 3, V3 is 2, 5, V4 is 8, 1. So, and I can determine that this set is linearly dependent. Right, so again, I can
Professor,
write down, yeah.
the rendering of your drawings are going in and out, and I can't read them.
Oh, okay, let me try. Can you read it now?
No, it still looks like an alien language.
Oh, okay.
There you
like
go.
The picture is not good, right?
It goes in and out. I can read bits and pieces.
Let me see. Is this better?
Yes. I can read that perfectly. It's a little, it goes a little blurry, but it's definitely more readable.
Okay.
Yeah, perfect, perfect. Thank you.
Yeah, right now it's good.
Yeah.
Yeah, I think I had like a weird setting. Yeah, well, let me know if it kind of goes bad again. But right now it's okay, yeah?
It's getting blurry again, but I think it might be your internet connection that might be going in and out. Or mine.
And it's probably mine. Let me see. All right. Yes, yeah, if it keeps doing that, I guess I could maybe restart the router or something. But right now it's okay, yeah? We're
Yeah, it's
still
okay.
back. Okay.
Will these also be posted later today?
Yes, yeah. So
Okay.
yeah, like after I'm done, I'm going to scan everything and put it up on
Perfect.
one of you. Makes sense.
Yes,
Right,
thank you.
so this example here, so I have 4 vectors, right? And maybe I did my augmented matrix and I determined that they're linearly dependent. Right. So if I look at the first two, 4 and 4, -1 and 3, remember for just 2 vectors, I can always look at are they multiples of one another. I mean, here, no, right? I have 4 and -1. I mean, V1 is V2 times -4, but 3 is not. Right? They're not multiples of one another by inspection. And V1 and V2 is a linearly independent set. So linearly independent set V1 and V2. So the first 2 vectors, but between each other are linearly independent. But when I look at my third vector, V3 here, I can actually write down V3 as a linear combination of V1 and V2, right? So if I solve for the constants, I'll get like 11/6 here and 3/4. All right, so my 11/6 times V1 plus 3/4 times V2 is going to be equal to V3. All right, so V3 is the linear combination of V1 and V2. That makes sense? All right, so let's look at okay, I mean, I'm not gonna ask you to do well, maybe it's still simple proofs, but I mean, it's not like a proof space. Like, it's not a class focused on proofs, but some proofs are, I mean, it just gives you more insight into why certain theorems work. So we'll go through some of them, and I think this theorem is kind of a good example of where it's good to look through the proof. Right? So if I have a set of vectors, V1 through VP, right? And I know that S is linearly dependent with V1 not equal to a zero vector. So again, the condition is just because the zero vector kind of, I mean, you normally don't want to include zero vectors in your sets of vectors when you're trying to decide whether they're linearly independent, because the zero vector will always make a set linearly dependent. Because I can multiply a zero vector by non-zero scalar, and that gives me a linear combination where not all constants are zero. Right? So we're assuming that V1 is not zero. And this is equivalent to saying that some vector Vj in my set of vectors is a linear combination of the preceding vectors. So I'm kind of do this in two steps, right? Because it's if and only if statement. So we can do one direction and then we can do the other direction. So one direction is if suppose some vector Vj, right? So some vector between V1 and Vp is in fact a linear combination of the preceding vectors, then my vector Vj can be written down as constants multiplied by those preceding vectors, with not all of those constants being zero. Right? And then all I'm doing here is I'm basically just putting Vj on the other side of the equation so that all of my vectors are on one side, and then since I'm removing this from here, I'll have zero on the other side. All right, so this just basically gives me Vj with -1 coefficient, and since I'm moving it to the other side. But looking at this is exactly my linear dependence relationship. All right, so this is my linear dependence relationship, and that means that my S is linearly dependent set. So kind of going in this direction is pretty straightforward. All right, linearly dependent set. I mean, going in opposite direction, well, we assume that V1 is not equal to zero, right? I mean, if V1 was equal to zero, I mean, this is just not a very interesting case because I will always have kind of a trivial linear combination, right? My V1 is zero, so I can always write it down as zeros times everything else. So it's not a very interesting case. But when V1 is not equal to zero, right? And my set S, I know that it's linearly dependent, because when it's linearly dependent, I know that there exists weights, so I'm multiplying by all of my vectors that are not all zeros, where I can write down this linear combination equal to zero. So to show the right-hand side, or to show in my theorem that, right, for some Vj, I can rewrite Vj as a linear combination of the preceding vectors. That's what we're trying to show. So if you look at this linear combination, then, I mean, you can solve for the values of those constants, and then just pick j to be the largest subscript so that Cj is not equal to zero. Right? So maybe, you have like 3 times V1 plus 4 times V2 plus 3 times V3 plus 0 times V4 plus and so on. So my largest subscript, so that Cj is not equal to 0, is going to be over here, right? All right, and then again, kind of two cases here. If j equals to 1, so just the first coefficient here, so all of the others are equal to 0, right? It's still linearly dependent, right? Because I can find one C1 that's not equal to 0, where everything sums up to 0. But this is also not kind of the slightly degenerate case because, all right, if I only have one 0 coefficient, I'm multiplying it by V1 and getting a 0 vector. I mean, if C1 is not 0, then V1 would have to be equal to 0 in order to get 0 here. But I'm assuming that V1 is not 0, so that's impossible. So I need to have kind of J, I need to go a little bit further in my set of vectors. So if J is greater than 1, then okay, I'm going to go through C1 times V1 all the way to Cj times Vj. And then this is my largest J, so that Cj is not equal to 0. The rest is 0, right? So basically, I can rewrite, right? I don't need that tail. And I can solve for Vj. I kind of skip this step. But I have C1, V1, right, plus all the way to Cj, Vj equals to 0, right? The rest is 0 coefficients. So if I solve for Cj, Vj, I will have minus C1, V1, minus C2, V2, all the way to minus Cj minus 1, Vj minus 1, right? And since by construction, I know that Cj is not equal to 0, I'm just dividing everything by Cj. Cj is not equal to 0 by construction. So Vj is minus C1 over Cj, E1 minus C2 over Cj, E2, and so on, minus Cj minus 1 over Cj, Vj minus 1. All right. But what we have here is exactly the form of the linear combination, right? My vector Vj, some constant times V1, some constant times V2, right? Some constant times Vj, or Vj minus 1. So Vj is some linear combination of the preceding vectors. That makes sense? So we'll do some examples too for this. And the most important thing to remember here is just because the set is linearly dependent, it doesn't mean that all of the vectors are multiples of one another, like it is for the set of just two vectors. All this means is that there's maybe one or more vectors in the set that can be expressed as linear combinations of some other vectors in the set. Right, and it could be just one vector like this, a couple vectors like this. We don't know just by kind of being given that the set is linearly dependent. Makes sense? We can do one more intermediate theorem here. So, and this can be extended to more than just two vectors, but suppose I'm looking at span of any two vectors, u and v, which are linearly independent, right? So if u and v are not multiples of one another, they're linearly independent. And if I look kind of geometrically at this, so I'm just going for simplicity, I'm going to take two vectors with, I mean, they're vectors in R3, but I'm going to take like 0 last component just so we can visualize it on kind of x1, x2 plane, right? So those two vectors are not multiples of one another, right? Because 3, I'll have to multiply v by 3 to get 3. And here I would have to divide v by 6. So those two guys are not multiples. Of each other. So they don't lie along the same line. And if I'm looking at the span of those two linearly independent vectors, my span is going to generate the plane through the origin. And here, because I took the 0 last components, is going to be kind of plane coinciding with the x1, x2 plane, right? So when I kind of drew this picture twice for the same UV, right? I have span of UV as a plane, span of UV as a plane, right? So if another vector W belongs to span of U and V, that means that this W lies in the plane of U and V, right? So we did this before. So if W belongs to span of U and V, W lies in the plane spanned by U and V, right? But if W does not belong to span of U and V, that means that W is just, it does not lie on a plane, it's kind of pointing at some different direction. Right, so W in a span means W is in a plane generated by U and V, and W not in a span means that W is not in the plane generated by U and V. Right? So how does this relate to our linear dependence and independence? If W lies in a plane spanned by U and V, that means that I can express W as a linear combination of U and V. And if I can express W as linear combination of U and V, that would mean that my set U, V, and W is linearly dependent, right? Why? Because if W belongs to span of U and V, that would mean that there are weights, say x1 and x2, not both equal to 0, such that my W equals to x1 times U plus x2 times V. If I put everything on one side, this would be W minus x1 U minus x2 V equals to 0, right? This vector equation has non-trivial solution. Right, and if it has non-trivial solution, that means that my set, right, U, V, W is linearly dependent. That makes sense? Well, I'm kind of going in the other direction too, right? If this is linearly dependent, right, then I have a non-trivial solution and I can kind of express one in terms of the other. But you can also look at the case if W is not in the span of U and V, that means that W cannot be represented by linear combination of U and V. That makes sense, guys? I mean, it's more like to understand it conceptually, how it can go, how those two concepts are equivalent, right? So if I have a set of vectors that are linearly independent, and I add another vector to this set that belongs to the span of the first two, I'm basically making my set linearly dependent. That makes sense? Yeah. So let's do another theorem here. So that one is pretty useful for when you try to determine if sets of vectors are linearly dependent. And it basically says that if a set contains more vectors than there are entries in each vector, then the set is linearly dependent, right? So if I have a set of P number of vectors, and those vectors are vectors in Rn, then the set is linearly dependent if P is greater than n. So if number of vectors is greater than the dimension of those vectors, then the set will have to be linearly dependent. So you don't have to do the segmented matrix form or anything else. You can just immediately conclude that the set of vectors is linearly dependent. And why is this true? I mean, you can, again, conceptually, we can think about it. So when I'm checking my linear dependence or independence, right, I'm basically forming my matrix A with columns corresponding to my vectors in the set, right? So first column, V1, my second column, V2, right, all the way to VP, right? So my matrix has P columns, but because my vectors VI belong to Rn, they will have n components, right? So I will have n rows, right? And remember, when we're solving matrix equations or systems of n equations in P unknowns, right? Number of columns tells me how many unknowns I have, right? Remember, when we're translating our right, A1, X1 plus A2, X2 plus dot. Number of unknowns gives me number of columns, but number of rows gives me number of equations, right? So n is number of equations, and P is number of unknowns, right? So if P is greater than n, that means that number of variables I have is greater than number of equations, right? So number of variables, number of unknowns is greater than number of conditions that are given. And in that case, what I'm going to have is I am going to have some free variables, right? I mean, in order to solve a matrix equation or a linear system for one unique solution, you really need to have same number of conditions as you have number of variables or unknowns. And not only that, I also need to have like pivot positions in every row, but kind of the necessary condition is, right, if I'm trying to solve for 3 unknowns, I better have 3 conditions or 3 equations. If I have 3 unknowns and only 1 or 2 equations, I will end up with a case where I have infinitely many solutions. Right. So, I mean, this theorem is basically conceptually this, right? It basically tells you if number of equations is less than number of the unknowns, right? Then what's going to happen is that my system will have non-trivial solutions. And if the system has non-trivial solutions, then it cannot be linearly independent. The columns of A will have to be linearly dependent. That makes sense? And this makes it really easy to kind of weed out some of the sets of vectors as linearly dependent without doing any, like, too much work, right? So for example, if I have a set of 3 vectors here, and those 3 vectors are vectors in R2, right? So if I was going to right now kind of start solving for this, my augmented matrix would be 2, 1, 4, minus 1, minus 2, 2, 0, 0, right? I have much more columns than I have rows, right? So I don't even really need to solve this because I know that I'm going to have 3 variables, right? If I made this into a square system, this basically means I'm kind of missing some rows. So I have rows of all zeros, right? So I'm missing pivots in some of the columns. So kind of what's really useful about this theorem is that you don't need to do this augmented matrix computation. You can save yourself some time and just state the theorem. Because I have n equals to 2 vectors of dimension 2, and I have 3 of those vectors in my set. Because P equals to 3 greater than n equals to 2, that would imply that my set has to be linearly dependent. There's no way I can have a linearly independent set of 3 vectors in R2. So by theorem. Make sense? But it doesn't really work in the opposite direction, right? So for P greater than n, yes, I can conclude the set is linearly dependent, but I can't really conclude it doesn't have to be linearly independent just because P is less than or equal to n, right? So I can have like a set of 2 vectors in R3, right? I have 2 vectors of dimension 3, and it could be dependent or independent. So you would have to check for this. So in other words, my theorem really only applies to the case when I have number of vectors more than the dimension of the vectors. And then I can conclude that it's linearly dependent. That makes sense? Too bad. One more theorem here. It also kind of saves you a little bit of time. So if I have a set of vectors in Rn, and that set of vectors contains the zero vector, then that whole set of vectors is going to be linearly independent. So again, remember, for the set of vectors, it just only takes one bad apple. So if only one vector, that's maybe a linear combination of some other vectors in a set, or even if I add just the zero vector, then it's going to make the whole set linearly dependent. All right, and again, you can kind of analyze it by using the definition, right? So I mean, zero vector could be any one of those, but kind of linear dependence, the order really doesn't matter. I can always renumber my vectors and say, well, maybe my V1, the first vector is zero vector, right? But if I write down linear combination, since V1 is zero, I can multiply it by a non-zero number in order to get zero. All of the other coefficients could be zero, but by definition of linear dependence, really I only need one of the coefficients to be not zero. And because coefficient of V1, which is the zero vector, is non-zero, then I have a linearly dependent set. So, and if you're trying to determine, like this example, 2, 3, 5, 1, 1, 8, 0, 0, 0, I have three vectors of dimension 3, but I can immediately conclude that because this is a zero vector belongs to my set S, my set S must be linearly dependent. All right, so again, just saves you some time. Examine your set of vectors. If you notice there is a zero vector in that set, your set will be linearly dependent. You don't have to do anything else. Makes sense? Some examples here. Again, just examine things first before doing any kind of complicated computations. What do I have here? Is it linearly dependent or independent on what we've done so far? So what do we first want to look for? Do we want to start writing down the augmented matrix form and augmenting zero column? I mean, we'll get the same answer, but it's going to take a lot more time. All right. In this case, we can look at the theorem we did earlier. What is the dimension of my vectors and how many vectors do I have? Right, so that was this theorem we did. My vectors here, V1, V2, V3, and V4 are all vectors in R3. Right. And how many vectors I have? I have 4 vectors. Right. So is it possible for the set to be linearly independent? No, right? Because I have more vectors than the dimension of the vectors. Right? So this has to be linearly dependent. Because I have basically kind of having 4 variables and only 3 conditions to solve for those 4 variables. So I will have some free variables, and meaning I'll have not just the trivial solution, but infinitely many non-trivial solutions to take linear combinations. So this set will have to be linearly dependent because number of vectors is greater than number of variables, the number of, can see the dimension. Number of vectors is 4, and dimension of vectors is 3. Right, so you don't have to do anything else. Conclude linearly dependent. So another example, also here, you can write down augmented matrix and start solving this, but for the case when you only have 2 vectors, there is also a little shortcut, right? Remember, for two vectors, you can just do it by kind of just examining whether those two vectors are multiples of one another. If multiples of each other. All right, so in this case, I mean, I can just look at the simple components maybe. It's like 4, 6, 6, 9. All right, if this is my V1 and this is my V2, all right? So for, say, my third component, I would need to multiply, or maybe let's do this component. So 10 and 15, 6 and minus 9, all right? So for this one, what do I need to multiply V1 by to get minus 9? Right, I will have minus 9 over 6, right, or minus 3 over 2. Yeah, so I'll have kind of component of V1 equals to minus 6. So third component of V1 equals to 6. Now I would have to multiply it by minus 3/2 in order to get minus 9, right, which is my V2 third component, right? But in the fourth component, if I take V1 fourth component equals to 10 and multiply it by minus 3/2, then I'm not going to get 15, right? I will have a negative value. Yeah. So I'll get negative 15, which is not equal to 15. So my V1 is not a multiple of V2, right? So V1 is not equal to alpha times V2 for some alpha. And since they're not multiples of one another, then V1 and V2 linearly independent. That makes sense? So kind of you have those few shortcuts, right? If you just have two vectors, just examine whether they're multiples of one another. If they are, dependent. If they're not multiples of one another, independent. If you have larger sets, what you can do is look at dimension of vectors and look at how many vectors you have. If you have more vectors than the dimension, then you can immediately conclude linearly dependent. And another shortcut is if you have a zero vector in your set, right? So if you have a zero vector again, automatically it's going to be linearly dependent set. So you're gonna test those three conditions first before starting to do your augmented matrix with elementary row operations. Right, it's longer. You can do it on all of those cases and get the same solution, but it's much easier just to use those shortcuts, right? And you have 3 of those. Make sense? Questions? Yes, no, no good. All right, so now the last thing, kind of going into, if I have a set, so here I have a set of 4 vectors, U, V, W, and Z. Can I determine if it's linearly dependent or independent? And first, maybe I'll look at just combinations of all of those vectors. So if I take U and V as the set, if I take U and W, if I take U and Z, if I take V and W, V and Z, W and Z. So I'm taking just kind of like all of the different combinations of 2 vectors from those 4. If I have just 2 vectors and I'm trying to determine whether they're linearly dependent or independent, just look at other multiples of one another. U and V, are they dependent or independent? All right, so here 3 minus 6, I'll have to multiply by minus 2. But 1 is not 2 times minus 2. So those guys are independent. Independent. U and W, right, also independent because they're not multiples of one another. All right, -4, 2 times -2 would be -4, but -5 times -2 is not 2. So this is also independent. U and Z, the same thing, 3 and 3, 2 and 7, independent. All right, V and W, 6, 0, 1 minus 5, independent. All right, so again, just for two vectors by inspection. All right, 3 and -6, 3 times -2, -6, but 7 times -2 is not 1, so independent. W and Z, 3 times 3 and 0, 7 minus 5, also independent. All right, so for two vectors, just multiples of each other or not. Then that tells you dependent or independent. So in this case, it looks like if I take any pair of two vectors in the set of 4, between each other, they're all independent. If I take all 4 of those, is this going to be dependent or independent? Remember our theorem, I have 4 vectors of dimension 3 because I have 4 vectors greater than 3 dimension. By the theorem we had earlier, the set has to be dependent. Right, by theorem. So what we can conclude from this, if I have a dependent set, if I have a linearly dependent set, it doesn't really tell me much about if I'm start taking subsets of those vectors. So I can have a linearly dependent set of vectors where pairwise, all of the pairs of vectors are linearly independent. Right? And then another thing I can do is I can look at, well, this is my set of 4 vectors. What if I looked at all of the pairs of different vectors. What if I start looking at the triplets of those vectors? So I know the set of 4 is linearly dependent, but what if I just take the first 3 of those? So if I take U, V, and W, is this set going to be linearly independent? How do I do this? Well, in this case, because I have 3 vectors of dimension 3, I can no longer use this shortcut of, too many vectors of too little dimension. So in this case, I would have to do it with putting my 3 vectors as columns in my augmented matrix, augmenting the 0 column because I'm trying to basically solve this vector equation and determine if it only has the trivial solution. So I'm forming my augmented matrix, I'm doing my elementary row operations. If I do this, I get to my row echelon form, from which I can find that my x3, x2, and x1 all have to be equal to 0. So because I only have the trivial solution, my set is going to be linearly independent. So the set U, V, and W, if I ignore Z, is going to be linearly independent. But that also means that because UVW was independent, then when I added Z, it became linearly dependent. That means that I basically added Z that already belonged to the span of the first 3. And that doesn't mean that it's expressed in terms of all 3. It could be expressed in terms of 1 or 2 or something like that. So my vector Z is in a span of those 3 linearly independent vectors. And I can basically solve for the constants that give me the linear combination, right? So if I take U, V, and W as my columns, and I join the column that is the vector Z, right, 3, 7, minus 5. Solve the system, this basically gives me the values of the weights when I'm writing down my linear combination. All right, so my Z will be equal to C1 times U plus C2 times V plus C3 times W. Right? So if I solve for those constants, right, basically I'm getting Z equals to C1 is 3 times U, C2 is 1 times V, and C3 is 0, so I don't have my W in my linear combination. So Z is going to be a linear combination of U and V, right? Z is 3 times U plus V. That makes sense? So again, kind of be careful with this, just because the set of all of the vectors is linearly dependent, absolutely does not mean that individual vectors are dependent, because all of the individual vectors pairwise could be independent, right? Here, U, V, and W are independent, so it's really the bad apple here would be this vector Z. Right? When I'm adding Z to the set, I'm basically making the whole set linearly dependent because Z is already in a span of the first three. All right, and it doesn't have to be Z either, right? So if I kind of renumbered or kind of switched my vectors a little bit, right? So maybe instead of taking U, V, W, and Z, I took Z, W, V, and U. All right, so I just reordered it a little bit. And instead of taking U, V, and W as 3, now I'm taking Z, W, and V. All right, and the same way you can show that kind of using my augmented matrix with augmented column 0, right? If this matrix, if this vector equation equals to 0 has only the trivial solution, which it does, right? So my set of Z, W, and V is linearly independent. Then by adding U to the set Z, W, and V, I'm making my set linearly dependent. That means that U is already in a span of the first three. And just like we did before for Z, we can do this for U, right? We can actually solve for the constants in the linear combination. So U in a span of Z, W, and V, right? We can basically use again our augmented matrix where augmented column is my vector U, right? I can solve for my constants. So again, I'm getting that U equals to C1 times Z plus C2 times W plus C3 times V. All right, solving for C1, C2, C3, I'm getting what my linear combination for U is, right? So U will be equal to 1/3 times Z minus 1/3 times V. That makes sense? Yeah, it's kind of recap. Like this whole example, we had four vectors. Four vectors by themselves are linearly dependent. Pairwise, everything is independent. Right? If I start taking three vectors at a time, they're linearly independent. And basically what happens is when I have three vectors that are linearly independent and I add a vector to the set that is already in a span of the other ones, then I'm making my set linearly dependent. That makes sense? So again, it's not a really complicated concept, but if it's the first time you see it, it takes a little bit of absorbing and maybe doing some homework problems, but I think you guys should be okay. But if not, we can maybe do some more examples, but we will be coming back to this concept over and over throughout the whole semester. So you should be okay. But any questions on this stuff? So we finished 1.7. You guys have questions on this? Make sense?
No, it makes sense to me.
Maybe a little bit of practice. Again, like the main thing here that I think people get confused on is, when you're talking about linear dependence or linearly dependent sets, it's really, it doesn't mean that all of the vectors are linearly dependent between each other. And in this case, it's really just like addition of one vector that makes the set linearly dependent. Right? If I take just three, it's linearly independent, but adding that fourth one is what makes it linearly dependent because that fourth vector is already in the span of the three other ones. Yeah, makes sense. All right. So if no questions, I guess I'll see you guys next time, and then with yours, I'll go through your quizzes now. And I think someone asked me to extend quiz 2, so maybe I'll extend the date for quiz 2. Otherwise, yeah. Was everyone good with uploading the PDF file for quiz 1? Is anyone still having trouble with that? No? All right, well, I guess I'll see you guys next time then.
Thank you, Professor.
Thank you, Professor.
No problem.